So I'm gonna, we'll go to slide 18. So we're gonna start off that for those who are following with the slides. Can you guys see my screen?
Yep.
Okay. It says equilibrium calculations. Calculate the equilibrium concentration for all the reactants and products if 0.5 moles of IC of iodine chloride is placed in a 5.00 liter flask with a Kc equal to 0.110. Okay. So we already have the equation set up for us. We want to make sure that the equation is balanced. Is the equation balanced? See or no?
Yes.
Okay, good. So we know that the equation is balanced. So what is our given? Let's see. Sadie, what are one of my givens here?
Aren't you given like the mole
mole?
and
The mole, okay. So we're given the moles of the ICL, right? And we're also given the volume. So right now, can we calculate the concentration? Because what is concentration? What are the units for concentration? Alberto, what are the units for concentration? What are some of the units for concentration? We're talking about concentration.
Is it moles per liter?
Moles per liter, which is molarity, right?
Yeah.
So big OM equals moles per liter. So we can calculate the concentration, right? So then we know that we have the given concentration or the starting concentration of the ICL, right? So we have 0.500 over 5.00 liters. What is that? 0.100 molar. Okay, so we also know that we need an ICE table. What does ICE stand for?
Like the chemical?
No, not the chemical, the abbreviation, ICE.
Something concentration, and I think is it equation or equilibrium?
Okay.
All right, ignore me. I don't know. I just remember they're a pain in the butt.
Yeah, so the last one was equilibrium. What is another word of saying in the beginning?
Initial.
Initial. Okay, so we know our initial, right? So we know our initial is 0.0100 molar, right? And we know that initially we're starting off with 0 of these components because we just started putting this in on its own initially, right? So then what do you think C stands? Think about President Obama.
it rhymes with range?
Come on, you guys can do it. I know it's Monday. The coffee haven't kicked in yet. You didn't put the IV of coffee in yet.
The range, what? Hold on.
It rhymes with range. And I said, think of President Obama, his campaign.
I don't pay
based upon
attention to
Change?
politics.
Change, okay? So the
Oh.
change. So we know that there's going to be a change that's going to be associated with it, right? So we have to sit there and take into account the change. So we know that we're going to have equal amounts of these guys since they're going to be 1 to 1. And X is going to represent change, okay? So then at equilibrium, this guy is going to be this amount minus the amount of change, right? And then these guys are just going to be okay. Are you with me?
Yes.
Good. Okay. So if we sit there and we work the equation, we know the equation is going to be, what is the equilibrium equation? Are you with me? I know it's Monday. It's all that hard drinking, celebrating with mom. I know you guys all got vaccinated, so you're being social.
What was the question again? Can you repeat it?
So the question is, so what is the equation for chemical equilibrium? In this case, for this particular problem. Come on, and you guys brush off those cobwebs.
So we don't know. Would it be the Kc equals the K equilibrium?
That's right, Kc. Well, Kc
Um,
equals,
oh.
that's going to be our equilibrium.
Well, because we got to find it, right? Because we don't
Okay,
know
so
the.
yeah, how will we calculate it?
Would you just divide by the initial? No. It'd be the equilibrium over the initial? Okay.
Okay.
Someone
So
help me out.
just give me the general equation first, and then we'll worry about the ice part of it.
Oh, man. Isn't it the
A
K?
plus B equals C or something.
Well, generically, if we had A plus B yield C plus D, we would have Kc equals, and then let's say X, not X, we'll use, hold on, Ma plus Nb yields XC and YD. So why is it important that we put those coefficients? So somebody was right when they said, so is it going to be products over reactants, or is it going to be reactants over products, or is it going to be? Okay, so I'm going to give you this one. So we know that it's going to be our products of our reactants, right? So our products in this case would be the concentration of A, boy, it was a rough weekend, wasn't it? Time the concentration of B to the nth power and B to the nth power. You guys remember this?
Yeah, I was trying to do it off memory. Now I'm trying to find my notes.
Okay, so what is it going to be in this case? What is it going to be in this case?
So we have final, right? So we just need final and initial. So we need to know and solve for B, right?
Okay, so first off, let's write the general equation for this particular equation. That's the first thing that you want to do. What is going to be our general equilibrium equation? We know that K represents equilibrium constant. It's going to equal what? Let's see. See, Cassie's been the only one to answer. Kayla, help me out here. What did we just say? In the case of our generic equation here, this was what the equation looked like, right?
Mm-hmm.
So what is it going to look like for this specific equation?
You know, I would love to answer this, but I'm kind of behind and I'm not really sure.
Okay, take a look at it, right? Look at it. Look at the chemical equation here. I mean, it doesn't take a brain surgeon. Just take a look at it. Look at the
Okay.
equation here. This represents the chemical equation. This represents the equilibrium calculations or equation. So Kc equals, can you see my little redness over there in the corner right here?
Yeah.
Okay, look at this chemical equation. So what do you think we're going to do in this case? Oops, actually, and I'm giving it to you wrong. Let's have products. There you go. This is what happens when you have that long weekend, right? There we go, right there. Okay, so this is the equation here, right? Products over reactants. So what do you think this is going to be for this equation right here?
Would it be flipped the other way around?
Is it going to be flipped, or is it going to be the same thing? Look
Or-
at this.
or
This
the
here
same.
represents the generic equation, right?
Yeah.
Generic, right?
The
What is
same.
my products here? tell me what my product is.
Iodine and chlorine.
Iodine and chlorine are my products. So that's going to be on top, right? Of the equation. Is there any coefficients in front of there?
No, because they're all
No.
single.
They're
Oh,
all
two.
Okay.
No.
So in this case, we just have the concentration of iodine and the concentration of chlorine. Now you guys don't have to make it hard, you know. You have the equation, just follow the standard. Products over reactants. Okay, so then what's going to be at the bottom?
It would be the two
Iodine chloride.
iodines and two chlorines.
So it would be the iodine chlorine.
And then you'd go to the second power.
That's right, to the second power. Okay, that's it, right? So that's the same thing. The coefficients become the exponents for the equation. Not too hard. Don't make it harder than what it is. You know, if you're given an example, take advantage of the example. Okay, are you guys with me?
Yeah.
Yeah.
Anybody ready to jump off bridges?
Yeah. I'm just kidding.
No, I want to hear no, there's no jumping off bridges. I'll put you off, but you can't jump off. You understand?
Thank you.
Okay, yes, because I care about you, right? Okay, so now we have the ice table, right? And so we know that equilibrium, we're saying that this is happening at equilibrium. We know the constant, right? They're giving us the constant. So then we just plug in our X values and we solve for X, right? So what are my X values? What are my values for equilibrium that I'm solving for?
So your I2 is 0.100 M.
Okay,
Your Cl2 is 0.
wait. Is that going to be my value? Because do we know the actual value at equilibrium? Do you know it?
Oh, no.
So remember, this represents equilibrium. That's why we put that big E there for ice. So we use
Okay.
these equations to plug into our values, right?
Okay.
Because we're looking at it at equilibrium. We're saying, okay, we reach equilibrium. This constant is only valid at equilibrium, right? So we know that at equilibrium, we're going to lose X of our ICL, right? And then at equilibrium, these guys are going to gain. Does that make
That's
sense?
right. Yeah, I remember now. Okay.
I know it was a long weekend. Oops. So we plug in those values, right? So we plug in our values for equilibrium, 1.00 molar time minus X, and that's going to be squared. And then we have X times X at the top. Okay, you guys see that?
Yeah.
Okay, so at equilibrium, right? So we know that this is at equilibrium. We have a value for Kc. So we can put in our Kc value and 0.110. And then we just solve for X, right? So the one thing that we can do, right? We can make an assumption. We're going to say, oh, you know what? This X value is probably really, really small, right? And if this X value is probably really, really small, kind of based upon what we're seeing here with this value, right? Then we can sit there and make the assumption that there's not going to be too much an effect on this. It's all going to be taken care of up here. That may be wrong, which we're going to find out here in a second. So then we
Was
can
it-
just x squared. Go ahead.
Dr. Henry, was it under 5 or under 5%?
It's 5%.
We can make the assumption.
Yeah. So
Okay.
yeah, you can go
Okay.
through and if your value is under 5%, then you're doing pretty good. Right? If it's greater than 5%, then you have to take into consideration this value, and then you'd have to do the entire thing. And if you actually take a look at the value, sometimes you can get an idea, right? So like this value here, this number is pretty large, relatively speaking, compared to like, let's say the last one, which was I think it's like 4 point something times 10 to the minus 5. You know, so then that probably means that you know, maybe this guy's going to be a little bit more expensive. I have to take it into consideration. Then I'd have to solve the equation, right? The full equation, which probably is what we're going to end up having to do in this case. So I'm going to assume that this value is going to be minimal. The x value is going to be minimal, that it's not going to affect the change of this value too much. So if I make that assumption, then I just have 0.100 squared, okay? Now we have to take into account these x values because we need to calculate that change, but it's going to give us a ballpark figure about where it is at, if it's the case, right? So if we go ahead and solve this, we have x squared. Anybody do the math for me? Where's my calculator? So we get x squared equal to 1.1 times 10 to the minus 3. And we get x equal 0.032 molar. Okay. Okay, so now if we have to go ahead and solve it, which is what you can do, in that case, let's see, we'd go through that process of using those values. Do you mind if I remove the ice table? Did you guys get the ice table written down?
Yes.
Okay, so do you guys remember how to do this? If I wanted to solve this part? Back in algebra, if I multiply both sides by the denominator here, if I multiply both sides by the denominator, this guy's going to cancel out and get the denominator over here. And what is that? Is it FOIL? Isn't that? When you do the multiplication?
Oh, yeah.
Yeah. Okay, so then we have 0.100 squared. Minus 2x, minus 2 times that value.
Minus x squared.
Would it be plus x squared, right?
Oh, yeah, because it's double. Yeah.
Okay, so then plug in our values there. Let's see. 1 squared. And that's going to equal x squared. So if we bring everything on the other side of the equation, we'll have 1 minus 0.11, which is going to be 0.89. Oops, sorry. 0.89 x squared plus 0.0022x minus 1.1 times 10 to the minus 3. So we have it set up as a quadratic equation or a second order polynomial so that we can use the quadratic equation to sit there and solve it. So let's see. You guys see my the little site that I put in the chat box?
Yeah.
The webpage, yeah.
Yeah. Okay, so we just put in the coefficients. So what is the first coefficient? What is A? Based upon that equation.
Was the 0.89 squared?
Okay.
And then 0.0022x
Okay.
and negative 1.1.
That's right. See if I can do it. Hopefully they'll accept it. Okay. Okay, so we had x could either be a positive value or a negative value. We know it's not going to be a negative value because there's nothing for it to take away from. So we know it has to be that positive value. So it's 0.03394. And what did we calculate using that short method? 0.0332 molar. So by us making that assumption, it's not too far off, right?
Right.
Oops. Okay. Okay, you guys see how it works?
Yeah.
Okay, cool.
Yeah.
Okay, so let's set this one up. And what is one thing that we always want to remember? What if I had instead of this being a gas, if it was a liquid, what would I do in that case?
Oh, what did you say about liquids and solids?
Anybody want to help her out? Abby,
Yes, what did you say again? Sorry. It cuts out the internet.
the question was, what did I say about liquids and solids?
Wasn't it their state?
What about their states? What is significant about the liquid and solid state?
I think the surface area for the solid, it changes. It's not accurate. Like you can't. Ah, what the heck, man? Of course, I only consider gas and aqueous solution, but I didn't put why.
Okay, so we know we only can consider gas aqueous solution. And it's because of that surface area, right? So they're gonna kind of, in terms of your equilibrium, they're gonna affect the equilibrium because they also affect. Okay, so let's go ahead and do this. In this case, this is all gases, right? So let's go into this equation and then we can start moving forward. Okay, it says calculate Kc with the initial concentration of 0.015 molar and then 0.0150 molar.
So for this one, would we set it up the same even though they're already giving us the equilibrium concentration?
That's right. We'd set it up, but are they giving us the equilibrium concentration, or are they giving us? They're giving us the initial concentrations. So they're saying you already have stuff in there initially, right?
Yeah.
This is what you put in initially, right?
Uh-huh.
So let's do our ice table. So our I would be 0.0150 molar and 0.0150 molar, right?
Mm-hmm.
Yeah.
Okay. So our C is going to be the change associated with that, right? And then our E is going to be
Equilibrium.
equilibrium, right? Okay.
So
So
under your N2, you would put the 1.96 in the E.
okay,
your
but that's
chart.
for, it says with an equilibrium concentration of N2 at this value. So that's our equilibrium concentration
For
That'd be
N2,
good.
right?
for
Yeah.
N2. Yes.
Yeah.
So it's going to be 1.96 to, oops, times 10 to the minus 3. Yep. Okay.
So then your H2O would be 0 as well.
It's going to start off at 0.
Yep.
And so this is going to represent our change. This is going to represent our X, right?
Yeah.
Okay. So now here is a little bit of that secret that is going to be going on, right? So we know that this guy here is going to be our initial, and we know that we're going to be subtracting our X. So we know what our X value is. We know what our equilibrium value is. We know how much is going to be removed from this chemical compound, but we also know that we have a relationship between this chemical compound, right? So we have a molar ratio that's going to be associated with it, right? Because we're making, for our X, for this total value, this is technically 2X. We also know that this guy is going to be, it's also going to be removing a certain amount, right? Which we were going to refer to as general X. right? But we need the relationship between these two items so that we can get it right. If we're saying this, that this guy is X, then this guy has to be, in terms of that molar ratio,
Would you do -6 or would you do -4?
okay, so there's a couple of ways of doing this, right? So if we could say this guy is 2x, because the value for this would be 2.
2.
This guy would be 6x. And then x can still represent the change that is being taken away from these guys, right? But we know that there's a relationship between how much we're taking, right?
Mhm.
That molar ratio. Okay, so this guy would be removing that 4x because it's 4, the amount. This guy would be removing that 3x.
Would the 3 be negative as well?
Yes.
Okay.
Okay, so then when we get our equilibrium constant, our equilibrium concentrations,
-3x, right?
we know that this is that value for 2x. And then we know that this here would be 6x, right? So the secret is here, we're trying to calculate the Kc, right? So we already know that at equilibrium, this guy equals 2x, and it equals 1.96 times 10 to the minus 3 molar. Okay, so then we know that x is going to be equal to what?
Shh.
I want to write stuff and it don't show. So x equals, what is that? 9.8 times 10 to the minus 4 molar. Okay, and then we just plug in at the values for it at equilibrium, right? So if this guy, if x is that, so then we go 6 times x in this case. Okay, so what is that value there? So that's going to represent the concentration of water at equilibrium. So we're just going to put EQ here. Okay, now what about these guys here? How would I calculate that at equilibrium? Matt,
Could you maybe talk me through it?
sure. So we know that this here represents our equilibrium value, I wanted to calculate the concentration at equilibrium, if I know the value of X, I solve for the value of X over here. I'm going to circle that in yellow. Okay, so I know the value of X. Can I calculate the value of the concentration of ammonia at equilibrium by using this equation? If I know what X is.
Yeah, you would just you would just plug that equation
Okay.
into X.
Or I plug in X into that equation.
Uh-huh.
Okay. So then I'll have concentration of ammonia at equilibrium is going to equal 0.0150 minus R4X. So 4 times 9.8 times 10 to the minus 4.
Mm,
Okay. Okay, working. Okay, let me get another calculator.
what was that 0.01108?
0.01. Okay, so 3 sig figs, it would be
0.0111.
that seems like a little much. Hold on. Let's see. Hold on. 9.8 e to the negative 4 times 4 minus. Okay, so, oh, yeah. So you're off by a factor of 10. So 0.00111 molar. And then what about the concentration of oxygen? Sadie, concentration of oxygen. How would I calculate that? Are you there, Sadie? Okay, Kayla.
Yeah.
Okay. So how would I calculate the concentration of oxygen?
0.15.
At equilibrium.
I don't know. I might need to.
Do you walk through it as well? Sure.
Yeah, please.
Hey,
Like,
so we know at equilibrium, this is going to be what the concentration of oxygen is. We know that we can calculate, or we calculate it at equilibrium, how much that X value is going to be, how much is going to be removed, because we knew that concentration of nitrogen at equilibrium was this. So we just solve for X, how much X is going to be transferred between all of the different chemicals, how much is going to be removed from each of the chemicals. So we calculated what X is. X is this. So if we know that this is the value of X, and this equation now for the concentration of oxygen is just going to be equal to 0.0150 minus 3x.
gotcha.
Okay, so do we not know what X is?
Yes, we do. So we would plug in the 9.8 times 10 to the negative fourth, right?
Okay, yep.
Which
So
would give us, where's my calculator? Sorry, let me plug it into my calculator. It's 0.0150 minus 3 times 9.8 times 10 to the negative 4. Oh.
okay, so we'll get 0.01251 molar for the concentration of oxygen. Okay, so now how do I calculate the equilibrium constant? Kc. Let's see, Cassie.
You would do your products over the initial, right?
Would it be products over my initial?
Or
products?
reactants, sorry, reactants.
Okay, so
So
what are my
then-
products?
So your products are N2, or it'd be N2
Okay,
to the second
Concentrate-
power,
the second power, okay,
and then H2O to the sixth.
okay,
Over NH3 to the fourth, O2 to the third.
and so do we have the concentrations at equilibrium now?
Yes.
Okay, so then we can just plug and chug.
Yeah.
Okay, so then what concentration for N2 was?
The 1.96 10 to the negative third. And that's gonna be multiplied by 6x.
Well, we already have that 6x solved, right?
Oh, sorry. Yeah, it's covered. Sorry, hold on. So the 5.8, yeah. divided by, and so the 0.0150. Oh wait, we solved that too, didn't we?
Yes,
Yeah.
we did.
Yeah.
0.01.
Yeah, 0.111 times the 0.0121. So,
Okay, so then we have our KC value.
um, so I got 2.04 times 10 to the negative 12. Don't know if that's right.
Okay, hold on. Let me see. Okay, you said 6 point what?
At 2.04 times 10 to the negative 12.
So I got 1, 2, 3, 4, 5. 5.90 times 10 minus 6.
Okay, let me try.
Anybody else plug it in?
Weird. 0. Six. 1. Just the answer. Yeah, I got a completely different number to the negative 14th now. So
14. Maybe try breaking it down, just do each one independently.
yeah, that's what I did this last time. I got each. So I took like 1.96 and I took all that to the second power. And I did the next one to the sixth power.
Okay.
And then I multiplied those two together.
And when you do like this value to the 6th power, did you put it in parentheses and so that you did the whole thing to the 6th power and not just the exponent to the 6th power?
I did the whole thing.
Okay,
So
so
I wrote the whole thing, like I put a parenthesis, wrote the whole thing to the negative third, parenthesis to the sixth,
okay,
right?
yeah. So like
Okay.
so for instance, when you did this guy, we squared it. That it's going to give you 1, 2, 3, 4, 5, 6. So that's 3.8 times 3.84 times 10 to the minus 6.
I got
Uh,
something completely different. I got
Well,
5.
For this first one.
Yeah, I got 5.669 times 10 to the negative 17th.
Okay, that's way too much if
Yeah.
it's squared.
Sorry.
Okay, so you got 1.96 EE to the negative 3.
Yeah, because I put it in this way. I don't know if you can see.
Let's see. I still can't see. Can you slide it over just a little bit? Yeah. Yeah. Okay, so close your parentheses before you go to the second power. Because what you're doing to the times 10th to the second power.
Well, I close it at the end.
I know, but that's what I'm saying. If you, okay. Let me see what you're saying again, please. So you have
Is the one at the bottom 0.011131?
so the one at the bottom is 0.0111 to the 4th power.
Okay, I'm plugging it in as well.
So let's see, Cassie, that very first number. So you're talking about this one here for the
Yeah.
concentration of nitrogen,
Yeah.
right? Okay, so you typed in 1.6, 1.96 to the negative 3. And then we're going to square that.
Oh, wow. I put to the 6th.
Okay.
There it is. All right. My bad.
Okay. Okay. And then the next one is to the 6th. So that is 5.88 e to the negative 3.
So I got 4.132 times 10 to the negative 14th.
Okay. 1 to the 6th.
I got, wait, are we supposed to get just a number or an equation?
No, you should just get a number.
Okay.
Times 10 to the negative 14. Okay.
Okay. And then I did the.
And then you divide that by
The fourth. 1.5 times 10 to the negative eighth.
One, two, 1, 2, 3, 4, 5, 6, 7, 8. So 1.5
Okay.
2 times 10 to the negative 8. And then times
1.77 times 10 to the negative sixth.
oops. That should be to the third here. I just screwed up internet. There, you said 0.01 cubed. Okay, so 1.77 times 10 to the negative 6.
Let me try this again.
Okay, so to make ourselves
Dr. Henry, I got 5.96 times 10 to the negative 6.
okay. 5.96 times 10 to the negative 6. I got 5.90 times 10 to the negative 6.
Okay, then. Well, okay, I'm off.
So, but no, that's close, Abby. It's close enough that you're probably an entering where I may have rounded once, you may have, or I may have rounded down, you may have rounded up, and that might have been the difference between the two. Does that make sense?
Yeah, that makes sense.
You're in the ballpark. Cassie, what about you? What do you got now?
I'm not even in the state of the ballpark. Holy cow.
Okay, so what I'd recommend, Cassie, do me a favor. Plug in just the numerical values right here. So plug in the numerical values. Don't worry about 10 to the power. We'll deal with that last. So plug in the 1.84, the 4.13, the 1.52, and the 1.77.
$6.28.
Okay, you got 6.28.
Yep.
Okay, try it one more time. So plug in, so 3.84 times 4.13.
Just that, or do you want me to divide it?
Just that.
15.86.
Okay, now hit divide 1.52.
10.4.
Okay, now hit divide 1.77.
5.89.
5.89. Okay, good. Okay, now if you look at the exponents, you have 8. So this is 10 to the 8th. This is 10 to the 6th. 8 plus 6 is going to be 14. So that's 10 to the minus 14. So then that's just going to cancel out this guy right here, right? And so then you're just left with 10 to the 6th.
Okay.
Okay.
What the heck?
Yeah, because what happens is that when you put it into the calculator, I noticed that if I'm not careful, if I hit like, because I use the term, it'll be XY, right? I use that term. So when I was putting things into the calculator and I was squaring it and to the 6th, it was actually just doing my exponent, not the entire thing.
Okay.
So my X value, they were looking at it as just the exponent. So the exponent was being, you know, to the 6th power. And okay.
Okay.
Okay, let me clear. Everybody got this, right?
Sorry, that took a while.
That's right. That's right. Okay. So I'm going to leave those last few for you guys to do on your own. And I recommend that you start trying to get them done. And also, you may want to start looking at the chapters of the book, because it's clear that you guys are not picking up what you should be picking up, and you're not remembering what you're remembering. But I'm trying to say this the nicest way without getting upset and throwing things and yelling and screaming, because I don't want to yell and scream because I'm hungry and I don't want it to amplify, right? But I am going to say, and I hope everybody's listening to this, right? I am going to say, I have no issues with you guys not passing the class. You know, I'll gladly see you next year. We're in that last leg. So you guys want to make sure that you start getting the understanding of this, because equilibrium is going to be a key part of most of your guys' career, whether you recognize it or not. A lot of you guys talk about homeostasis. If you're going into physical therapy, you need to be aware of equilibrium. You need to take this a little more serious than what you're taking, right? And I know that you guys, a lot of you guys, these are the last classes that you need. So don't dip out now. You know, you put too much effort into it. You put too much work into it. I know getting up at 8 o'clock in the morning is not the best thing to do. I don't want to do it. You guys don't want to do it, especially when we've had a late night and a long weekend. But reality is we have work to do. We need to step up. Are we clear?
Yes.
Cassie,
Yeah.
I know I hear you. I hear Abby. Are we clear, Abby? Are you ignoring me, Abby? Alberto, are we clear?
Yeah.
Kayla?
Yep.
Matt? Sadie?
Yeah.
Okay, I expect better. I'm just letting you know now. Okay, so I'm going to stop here. You guys are responsible for the rest of this chapter, and you're responsible for chapter 14. Chapter 14, we're going to be going over it, and we're going to go over it very fast. Chapter 14 and chapter 15. They all deal with equilibrium. They're setting up the same type of situations. Take a look at it. Start looking at it now. Okay?
Do you have the slides I can download?
I sure do. I'll put
okay.
them in the chat.
This last week was rough. I had final exams for the class, and it was
Probably
just taking
almost
up
all your
all
other
my
classes.
time.
So let me stop sharing so I can do it without crashing. Okay, maybe. Okay, here's chapter 14. Chapter 13.
Thank you. Thank you.
Chapter 15. Now chapters 14, chapters 13, 14, and 15, they all deal with equilibrium. They're just it becomes a little more specialized. One case, we're just talking about acid and bases. The concept is going to be exactly the same. Only thing, you get to make a little more assumptions to make your life a whole lot easier. That is the distinction between them all. But if you understand the simple basis of equilibrium and the equilibrium expression, that equation, right, and how to set it up, that's going to save you a lot of heartache because you can work your way through anything. Okay. Okay. I'll see you guys on Wednesday.